Good evening all. Welcome to live session 5 of Fundamentals of Convective Heat Transfer course. Hope my screen is visible. We'll wait for a couple of minutes for a few more students to join and then we'll get started. In the meantime, I think we can get started with the problem that we ended in the last week that I kind of left you as an exercise. You can go through the problem first. It's a transformer that is 10 centimeter long, 6.2 centimeter wide, and 5 centimeter high. Is to be cooled by attaching. So this is the transformer that you are trying to cool, and that is cooled by attaching a fin. Fin is an extended surface which has an area like this. It is assumed that the entire surface temperature, like the entire surface, including the transformer and the fins, are at 60 degrees Celsius. The ambient air is flowing at 25 degrees Celsius. And the question now is we need to dissipate a certain amount of heat. So for the temperature to be constant, the heat removal rate should also be constant. And that heat removal rate is given to be 20 watt. So under these conditions, if and neglecting the radius to heat transfer, determine the minimum free stream velocity the fan needs to supply so that you can avoid the overheating. So how would we approach this problem? We discussed already this last time. So the basic idea is the net heat transfer balance should be achieved. So we have the Q given by the heat transfer coefficient times the total surface area times the delta T between the surface and the fluid. And in this particular case, this surface temperature is given as 60 Celsius and fluid temperature is given as 25 Celsius. So next step is to calculate the total area from which the heat is getting transferred to the fluid. So this is basically the area where the fluid is in contact with the surfaces. Now this week we discussed about internal flows. Like in this week there is a concept on parallel plate channel flow. So here there is a separation between the plates is there, like it's not like a infinite external flow. We have a channel flow, but then as we discussed before, even within channel flows, if the separation distance between the plates, let's say the separation distance is given by the distance between from plate to plate, the internal distance is given by b. If 2 times the boundary layer thickness is greater than, sorry, is less than b, then you can actually use the flat plate assumption. So first we have to check whether the particular assumption is valid or not. So even before doing that, the first step for us is to calculate the heat. Q is given to us. So we need to calculate the H and A. So Q is given as 20 watt. So first, what is the total area that is being exposed? The total area of contact between the fluid as well as the, hi, good evening. So the problem that I am discussing now is we have a transformer that is generating a given amount of heat 20 watts. And the objective here is to find what should be the flow rate of the air so that we can achieve maximum temperature of 60 degrees Celsius on the surface of the transformer and the fins. So in this first step, we have to find the total area of contact between the air as well as the whatever the surface that from which heat is getting generated. So what is the total area of contact between air and the solid? We can basically divide it into two components. The first area is basically the exposed area of the fins, that is the extended area of the fins, and the total base area, which is not exposed, like where only the transformer is in direct contact with the air. So if you see the fin here, so this, if I see the cross section of this, so you have fin like this, so on, we have 7 fins. So the total surface area will be this, all these surfaces plus the base area, which is also exposed to the ambient air. So how would that be? So in this particular case, we have 7 fins, and the area of each fin is, each fin will has 2 surfaces. So 2 times the surface area is, the height of the fin is given as 0.5 centimeter cross the length of the fin is given as 10 centimeter. Plus we also need to calculate the base area that is directly exposed to air, which will be, so because we have 7 fins, so it will be 6 bases into length is 10 centimeter cross what would be the width of each of this. So for 7 fins, the total length is given as 6.2 centimeter. So thickness of each fin is also given to us. Each fin thickness is given as 2 mm. So the total length will be, so we'll have 6 gaps. So 6 into the distance between each of these fins is, let's say, b, plus we have 7 fins times the thickness should be equal to 6.2 centimeter, right? And thickness is given as 2 mm, which is 0.2 centimeter. So if you substitute that, from that we can get the value of b. It's coming to around 0.8, 4.8 by 6. That is around 0.8 centimeter. You can compute this value. Once we have the area, the major point here is to determine the value of the heat transfer coefficient. How do we get that? How do I get the heat transfer coefficient? So for that I need to know the correlation between Nusselt number as well as Reynolds number. So we have the Nusselt number relation given by average Nusselt number is h times the characteristic length. The characteristic length should be taken along the flow direction, which is 10 centimeter, divided by thermal conductivity, where the thermal conductivity is given by mu Cp by Prandtl number. And the values of thermophysical properties you can take from whatever I discussed previously. I have given you the correlations for that, where mu is given by maybe I should have used different notation. So let's call this free stream temperature to be T infinite, and Tf is the film temperature. So from this you can calculate the value of mu, where film temperature is given by average of the surface temperature and the free stream temperature. So you can substitute that and get the value of mu. Cp you can take as 1006 joule per kg Kelvin, and this will be in Pascal second. And then Prandtl number you can take as 0.71. L is already given as 10 centimeter. You can substitute all these values, and then from this equation, from equation 1, Q is given as 20 watt, Ts and T infinite are known, and A value is also given. So you can calculate the Nusselt number, the heat transfer coefficient. Once you have the heat transfer coefficient, you can calculate Nusselt number. Now, as I said, now we will use the external flow concept, where we know the relation between Nusselt number and Reynolds number. which is given by 0.664 times Reynolds number to the power half and Prandtl number to the power 1 by 3. So first we'll calculate the heat transfer coefficient. So from Q you calculate H value, from that you calculate Nusselt number, you know the Prandtl number, so from that you calculate Reynolds number, and once you have the Reynolds number you can calculate, Reynolds number is basically U infinite times L by nu, nu is basically mu by rho, and rho you can use ideal gas law, P atmospheric times molecular weight by RT. And what temperature I should be using here? Yeah, film temperature. So I substitute that and get the density, and from that I can mu by rho is nu, so I can substitute that here, and from this I can get my U infinite. Yeah, I'll wait for a couple of minutes so you can do the calculation. Were you able to calculate the heat transfer coefficient first? So from first step, I got the heat transfer coefficient to be around, so Q is given as 20 watt. So once I substitute that into this equation, I got H value to be around 48.426 watt per meter square Kelvin. And from this I got Nusselt number. I'll directly show you the value of Reynolds number. So you substitute that into Nusselt number and get the value of Reynolds number, which I got to be around, and from this I can calculate U infinite, which is coming to around 15.5 meter per second. So now we have to check two more things. Once you solve the problem, we already made certain assumptions in order to solve the problem. Now we have to verify whether those assumptions are valid or not based on the solution we get. So in this particular case, this particular equation, the correlation that we use between Nusselt number and Reynolds number is valid for flat plate and laminar flow. So for a flat plate laminar flow assumption, this correlation is valid if the Reynolds number is less than 5 into 10 power 5, which is kind of satisfied in this case because the value of Reynolds number we got is less than this particular value. But the next assumption that we made is we used a flat plate correlation. However, we know that the flow here is actually looks like a channel flow, which means we have to further verify the next assumption where we have to verify whether if the boundary layer thickness is less than b by 2. So essentially you have the fins like this, and a boundary layer will develop on this fin, and we are verifying this is the total distance between them, and this is my boundary layer thickness. So we are checking if delta is less than p by 2. If that is happening, then we can see how far, like how good the approximation is going to be. So for that we have to first estimate the value of delta. And how do I do that? For which we already have the correlation. Delta is given by 5 times, and now we have to calculate this at where L is given as 10 centimeter. So 5 into 0.1, and that comes to be around 1.66 mm. While if you see the value of B is around 8 mm. So you can see delta by B by 2 is around, so it occupies less than 40% of this. So which means the assumption that using that it is a flat plate is a reasonable assumption in the present case. Are there any questions? I left this problem as an exercise last week. So if you have any questions, please do let me know. Okay, I guess there are no questions. Then we move on to a quick recap of what is discussed in this week of lecture videos. So this week we started on internal flows. What is the difference between internal and external flow? So in external flows up until now what have been discussed in the up to last week, where we have a flat plate and some free stream velocity is some flow is happening like this. Then immediately when this free stream sees a wall or some kind of an obstacle, you will have some kind of a shear stress, because of which there will be a velocity boundary layer that is getting developed. This is what we discussed up until last week. In this week, what we were seeing is now this is kind of an unconfined flow. So we also call this an unconfined flow or semi-confined flow, where there is a restriction on only one side of it. So this is a semi-confined flow. However, this week of lecture video discusses about confined flows, where you have two walls and then you have the same free stream as before. And what we are trying to understand is what happens as along in this domain. This is my fluid domain. So similarly, the first step during the initial phases, what happens is same as before. So we have a velocity boundary layer that is developing here and another velocity boundary layer developing here, and they will eventually meet at a point, and beyond that it will be a, like, boundary layers will be completely matched with each other. But the main difference between the flow here in this half of the domain and this semi-confined one is that here what happens is, you see, there is some kind of a convergence happening, because of which the fluid accelerates. If the fluid accelerates, then the velocity gradient is not equal to 0, and from Euler equation we have, from the Bernoulli's equation, we have p plus half rho u infinity square equals to constant, and from this we know the dp dx du infinity dx. So in the case of flat plate, we set u infinity is free stream velocity is constant. So du infinity dx is 0. Hence we were able to remove this particular term from the boundary layer equations. However, now in the confined flows, the fluid accelerates as we go into the free stream, in the streamwise direction. If the fluid accelerates, then du infinity dx is not equal to 0. So because fluid accelerates, this particular quantity is going to be positive, which means the dp dx is going to be negative. So there will be a pressure gradient in this region. Because a pressure gradient exists, we cannot directly use a solution that we already have before. So we will be developing a new solution in this region. So this region, till both the boundary layers merge, is called, let's call this LH, which is denoted by hydrodynamic entrance length. Now, we can use the scaling analysis, whatever we discussed in the first week or second week of lectures, to estimate what the scale of this LH is going to be. So as you see, the idea is this is similar to the scaling analysis, very similar to what we were doing in the boundary layer analysis. So this distance is more or less delta. So if we call the radius of this particular one is r naught, so this both of them should be of the same order, then you will have considered that the flow has entered into something called a fully developed region. Once it enters into a fully developed region, there is no concept of this boundary layer. The effect of wall is being seen throughout the fluid, then you call that a fully developed region. Here the effect of the wall is seen only in this region. Here it is seen indirectly due to acceleration of the fluid, but otherwise it's not seen here. Now, from the scaling analysis, we can actually get an estimate of LH. So we already know from scaling analysis that delta by x will scale as 1 by Rex to the power half. However, here Rex is defined with respect to length along the flow direction. In internal flows, the definition of Reynolds number itself changes. We use a different definition of Reynolds number, which is based on something called hydraulic diameter, which I'll define in some time, where this Reynolds number is given by U average, the mean velocity, times d is the hydraulic diameter divided by nu. So the characteristic length in case of internal flows is some kind of distance that spans between the two walls. In this case, if it is a tube, then it will be the diameter of the tube. Otherwise, there is something called a hydraulic diameter, which we will define in some time. And then, unlike external flows where we have free stream velocity, in internal flows we use a different concept. We use the average velocity instead of the free stream velocity to define our Reynolds number. So from this definition, we can actually relate with whatever we already have before. So delta is given by this. So this delta will actually scale as d, which is basically my diameter, and x will scale as the entrance length. And that would scale as Re times, instead of x, we'll be having LH to the power half, where ReLH is given by u times some velocity scale times LH by nu, which we can rewrite as u times d by nu times LH by d, and we can substitute this back here, and from this we can get a relation which states that LH by d by Red to the power half will scale as of order 1. Now the same concept we can also apply to temperature boundary layer, which is again discussed in detail in the lecture videos, which I am not taking up again. And there, instead of Reynolds number, say this, how did we get this Reynolds number? The Reynolds number is the one that characterizes the velocity boundary layer. Similarly, for temperature boundary layer, we would be having Peclet number. So in that case, we'll have the same thermal entrance length divided by the hydraulic diameter with respect to the Peclet number, which is Red times Pr to the power half, scaling as 1. This is what would happen in case of a thermal boundary layer. Now, we can also get an estimate of what is the ratio of the thermal hydraulic to the thermal entrance length, which will scale as the ratio of these two. So, LT by LH will scale as PR. Note here that previously when we were having the thermal boundary layer thickness with respect to delta, that was actually scaling as PR, Prandtl number to the power half. Sorry, this is delta t, so it should have Prandtl number to the power minus half. However, in this particular case, this is scaling to the power Prandtl, scaling as to the power Prandtl to the power 1. I think these are all already discussed in the lecture videos. This is just to kind of give you a brief overview. And as I said, this hydraulic diameter is also a concept that we'll be using, which is defined as the 4 times the cross-sectional area of the flow divided by the wetted perimeter, which is again, once we do a problem, this will be more clear. The major part of this week of lecture videos is basically in two kind of problems, where we have either a uniform heat flux it's called that UHF in an internal flow, or a uniform wall temperature. So these are the main two problems that were discussed in this week of lecture videos. So in the first case, we will be given a given value of Q double prime and will be asked to find wall temperature and a concept which we will also discuss called mean temperature. Just like mean velocity, we also have the concept of mean temperature or the bulk fluid temperature. So we will be given a heat flux and will be asked to find this. In case of uniform wall temperature, you will be given a wall temperature and you will be asked to find the heat flux and the mean temperature. So it's either one of these cases. So in this week, we did not derive, there is no derivation for Nusselt number, but we still get some meaningful insights as to, for example, in the case of a uniform heat flux, what happens is you have a wall that is getting uniformly heated from both the sides. You have some kind of a flow in which you are getting heated from the both sides. Then what you would expect is because you are continuously adding the heat, the wall temperature should keep on increasing. That is a straightforward thing. But from energy conservation, we can say that you are continuously adding the heat and that energy is getting continuously absorbed by the fluid. So the temperature of the fluid should also increase. So as X increases, your wall temperature increases and the mean fluid temperature also increases. However, if I were to plot this as a function of the streamwise direction, X, so then we will see that the mean temperature actually increases more or less linearly, while the wall temperature initially increases quite fastly and then eventually it settles down. And this distance, the Tw minus Tm, will actually be a constant. And this region beyond which this ratio becomes constant is called fully developed. The idea behind a fully developed one is because we can write the heat transfer coefficient just like when we were defining for a flat plate, we defined heat transfer coefficient as a we define heat transfer coefficient in such a way that the heat flux is related as delta T, where delta T is the surface temperature minus the free stream temperature. In this case, as I said, there is no concept of free stream temperature. We will only use the average temperature. So here it will be the wall temperature minus the bulk mean fluid temperature. And Tm is defined in a specific way where it represents the average energy of the fluid. So that will be U times T divided by UdA. So this gives you the mean temperature and from which we can calculate QW. Since for a uniform heat flux QW is constant, and as I said that in a fully developed, once we reach into fully developed condition, TW minus TM also becomes constant, which means heat transfer coefficient becomes constant. So that is the main thing. So H is constant. Under fully developed flow condition. Now similar arguments we can also do for a uniform wall temperature. Once we have uniform wall temperature, because TW is constant, initial fluid will have some temperature. Let's say it is entering with some temperature, mean inlet temperature TMI. Now what happens is this temperature is lower than, let's say is lower than the TW. Then as the fluid goes along the streamwise direction, it takes up energy from the walls and it gets heated up. Until what temperature it will get heated up? Eventually this temperature should reach the wall temperature. That's when it will get completed. Beyond that point, it will not be able to take any heat from the wall. So that is intuitively put, but then if we can also write it as an expression where the mean temperature initially starts from TMI, like, and eventually reaches that. So the temperature difference between wall and this gradually reduces, and that reduction is given by this exponential term. P is the perimeter times average heat transfer coefficient times x is the streamwise distance divided by m dot is the mass flow rate times Cp plus Tw. As x becomes infinite, this particular term becomes 0 and eventually you will reach the wall temperature. So that is the basic idea for a uniform wall temperature case. So if I were to plot same as what I have done before, in this case Tw is constant. So here this is Tw and this is Tm. In this case Tw is constant and the mean inlet temperature will start from some low value Tmi and then it will asymptotically reach the value of Tw. At infinite this will become equal to Tw. I should draw like that. So this is Tm value. So the difference between Tm and Tw will keep on reducing. So what happens to my heat flux, heat transfer coefficient? This is my Tm profile. So what happens to my heat flux and the heat transfer coefficient? As we can intuitively understand, as we go further and further away, the sorry, as we go further and further away, the temperature difference between TW and TM reduces, which means the fluid now has enough potential. So temperature you can think of as a potential to take heat from the walls. Now initially it has the temperature difference is high, so there is more driving force, so there is a more heat flux. But as we go along the flow direction, the temperature or the potential of the fluid also increases and becomes closer and closer to the wall temperature, which means the heat flux will keep on reducing as we go further and further downstream. So QW prime will keep on reducing and the temperature difference also reduces. So this means the ratio H, which is defined as the ratio of QW prime to TW minus TM, this becomes constant. This is another interesting property that we will actually take up in next week of lecture video, where you will actually observe that well, even if it is a uniform heat flux or a uniform wall temperature, the heat transfer coefficient is going to remain constant under fully developed condition. However, the constant value itself will be different for uniform heat flux and uniform wall temperature, but they are going to remain constant once you enter a fully developed region. But the heat flux will actually keep reducing. And then we also have the scaling relations for either of these cases. Once we reach a fully developed region, we know that the Nusselt number is related with a certain way, where the Nusselt number scaling is. We'll also write the Nusselt number scaling for fully developed region. Once we enter the fully developed region, we can write the Nusselt number like in fully developed versus the developing region. In developing region, we already know. We can use the boundary layer theory that we already developed, and from that we can write the Nusselt number will scale as Reynolds number to the power half. And interestingly, here it Prandtl number also to the power half. And then we have an extra parameter which is this is basically the x is basically the entrance effects. As x value becomes larger and larger compared to the diameter, then eventually there will be a point where the effect of this particular term is negligible, and then it will only depend on these two quantities. So this is in the developing region. Once you enter fully developed region, then we have a different scaling. What happens is this is in developing region. Once you enter fully developed region, what happens is this, as I said, the heat transfer coefficient becomes constant. In fully developed region, we have NUT defined as the heat transfer coefficient times d by k. As I said, h becomes constant in fully developed region, d is a constant and k is a constant, so this will be some constant. And the last part of this week's of lecture is on the plane Poiseuille flow, which you might have already learned in fluid mechanics. So this is a classic problem where you have two walls, and then you have some initial uniform velocity inlet at the inlet. Let's say this, call it as, this is my y-axis. The distance between these two parallel planes is 2h. So from the center axis it is h top and h at the bottom. So the problem now that we are trying to solve is what is the velocity profile in this region. We already know now for the fully developed flow, the velocity should not change after beyond a point. So we can apply the condition du along dx is 0. And from this we can write the governing equation. The Navier-Stokes equation reduces to, we do not have any inertia terms because in a v is 0, and then we also have u du dx equals to 0. So the only terms that are left are viscosity term is balanced by the pressure term. So this is the viscosity term which is balanced by the pressure term, and the boundary condition are at both the walls plus or minus h we have no slip condition. So once you solve this, you can actually get the velocity profile, which is a straightforward exercise in fluid mechanics. So I'm not going to repeat that again. And from this we can also calculate the mean velocity, which is defined as integral u of y. So mean velocity you have to integrate across the y from minus h to h, which gives us, so from this we can rewrite this as, we can also calculate the maximum velocity from this, which happens at y equal to 0, which is 3 by 2 um. So the maximum velocity is related to the mean velocity by this equation. Again, remember this is only for a plain Poisson flow. Once we move on to a flow inside a duct, or in case of a tube or something where you have a axisymmetric tube, then in that particular case this relation changes. So this particular constant is only for the case of flow between two parallel plates. So these are the ones that are basically discussed in this video. To quickly summarize, so first it starts out with what an internal flow is, and then we try to extend from what we already learned in the last week where external flow is used, but then we observe that beyond a point the approximations that we made in case of external flows, like the negligible pressure gradient or negligible velocity gradient, are not valid. So first we'll start with a case where what is the region in which these particular conditions are valid, and then determine these terms called hydrodynamic entrance length and thermal entrance length. And from the scaling analysis, we determine that this scales with Reynolds number, and this scales with Peclet number. The thermal entrance length scales with Peclet number, and the ratio of thermal to hydraulic entrance length will scale as Prandtl number. Subsequently, two different cases are studied. One is the uniform heat flux, the other one is uniform wall temperature. In uniform heat flux case, energy is getting continuously added to the fluid, the temperature will keep on increasing, both the wall and the mean temperature. Because heat is getting transferred from the wall to the fluid, wall temperature has to be higher than the mean fluid temperature, and this difference becomes constant. Then we call that particular thing as a fully developed flow. So in fully developed case, we have a constant heat transfer coefficient. Similarly, for a uniform wall temperature, the wall temperature is constant, inlet temperature is lower than wall temperature, then the fluid keeps on taking heat from the walls, and eventually the fluid mean temperature will become equal to wall temperature, beyond which it will not be able to take any heat from it. And the relation between mean wall temperature and the fluid temperature is given by this expression. So where the rate at which the rate at which the inlet temperature becomes equal to the wall temperature is given by, is dependent on the average heat transfer coefficient, the perimeter of the surface from which the fluid is in contact with the solid, the flow rate of the fluid, and the specific heat capacity of the fluid. And even in this case, the heat transfer coefficient is going to remain constant. Because the heat transfer coefficients are constant, the characteristic dimension is constant, and thermal conductivity is constant. The Nusselt number will also become a constant in fully developed cases. And then on the developing region, we also have to take into account the entrance length effects, which will scale in this particular fashion. Finally, the lecture ends with the plain Poisson flow, which we already know in fluid mechanics, which is kind of a prerequisite for this course. We'll actually solve some problems, and then these concepts will become more clear. So first we'll start with a basic problem where, as I said, we will start with unlike a plain Poisson flow, let's take you have a flow inside a pipe, circular pipe. Inner radius is given as 2 centimeter, and the velocity is given by this equation. So you have to find the mean and maximum velocities inside the pipe and the volume flow rate. This is a quite straight simple problem. So maybe you can take a couple of minutes and then we'll discuss. You can quickly solve this if you want the definition. So velocity is given by this equation. So how do I define mean velocity? Mean velocity is defined as integral the velocity at any location times the cross section area that I will be taking is 2 pi r dr from 0 to r divided by the total area. This is mean velocity. And how do I get maximum velocity? Maximum velocity is straightforward. From calculus, we can actually calculate dv by dr equals to 0. And from this, we find r value. Let's call r max, that particular r value as r max. And then we have to calculate the velocity at R max. In this particular case, it's actually straightforward. You can actually see the velocity profile, and from that you can say that velocity is maximum at r equal to 0. So r max will be 0, and from this it will be equals to 4 meter per second. This is a straightforward one. The mean value also you can calculate, and the final one is a volume flow rate. How do you get volume flow rate? Is velocity times area. So V of r times 2 pi r dr between 0 to r. Yeah. Take a couple of minutes and solve this. Yeah, I think you are done. So I got this value. Okay, I can calculate this here. So Vm is basically integral 0 to r. So that comes as and then volume flow rate is straightforward from this. This is quite simple and straightforward problem. And we'll move on to the next one. So here we have a thin copper tube and water is entering from it at 0.3 kg per second and 15 degrees Celsius. This problem is taken from Single book. That is also one of the reference textbooks for this particular course. The diameter of the tube is given as 2.5 centimeter and this is the outer diameter. Steam is present on the outside of the tube where it is condensing at 120 degrees Celsius. Because it is a condensing which is a latent heat transfer, the temperature is going to remain constant. So that is point number one, where because I'll just write like this, where you have condensation. So you can take this as uniform wall temperature. So now the question, as we already discussed, is initially water is entering at 15 degrees Celsius. Because this is a uniform wall temperature, the water will keep on take heat from the steam, and the temperature of the water will keep on increasing. So if I were to plot as a function of x, initially it will start at 15 Celsius, and eventually it has to reach 120 Celsius. It will go like this. It will actually be exponential. Something like this. So only when x tends to infinite, this difference between these two will become 0. So the question now asks you, okay, if the heat transfer coefficient is 800 watt per meter square, what is the length of the tube at which the temperature becomes 115 Celsius? So if I draw a line like this, where this is 115 Celsius, then what is this particular x value? So you can also think of it in this particular way. So like you know for sure that it will not reach 120 degrees Celsius unless you go to infinite. Like beyond a point, every meter of copper tube that you are going to use will add cost to you. So beyond a particular point, the benefit that you're going to get is getting reduced. For example, if you make X amount of money by condensing some amount of steam, then as you increase per meter by meter, the cost also increases, but then the amount of profit you are getting by condensing steam is getting reduced. So there is a limit where you have to stop. So here it somehow they identify that 115 degrees Celsius is acceptable for them. So at 115 degrees Celsius, if I have to reach 115 degrees Celsius, what is the length of the tube that I need to have? So first we can do an energy, simple energy balance. And so if I take a simple cross section here and I can write m dot Cp times the change across. So if I take a simple cross section here, then across this the temperature change is dTm, m dot is the flow rate, Cp is the specific heat, and that should be equal to, so the net heat transfer that is happening here should be equal to the heat gained or from the steam from either sides, which is H times the total surface area, which is P times dx, where P is the perimeter, times wall temperature minus mean temperature. So we can solve this differential equation, and H value is also already given to us, 800 watt per meter square. And perimeter you can directly find. Perimeter is basically the outer pi times outer diameter. So you can substitute this and solve this equation and find the, so basically if you have to solve this, so this becomes dTm by W minus Tm between the limits 15 Celsius to 115 Celsius Hp dx between 0 and L. L is the length that we are trying to find, where Tw is also given to us as 120 Celsius, m dot is given as 0.3 kg per second, Cp is here the flow water, so you can take Cp to be 4187 joule per kg Kelvin. What are the quantities do you require? D is also already given as 2.5 centimeters, so you can calculate perimeter and all the values are given to us, given to you. So you can directly find the length L. So what we are trying to find is length L. There any questions? Okay, take a couple of minutes and then solve and let me know. Yeah, did you get the value of length? So if you solve the above differential equation, you will get L as m dot Cp by Hp times ln of Tw minus Tm at the inlet by Tw minus Tm at the outlet. So if you substitute the values, m dot is 0.3, heat transfer coefficient is 800, perimeter is pi times diameter, you have to convert it into meter, times ln of the wall temperature is 120 Celsius minus the inlet temperature is 15 Celsius by 120 minus the outlet temperature is supposed to be 115 Celsius. If you solve this, I'm getting this around approximately 61 meter. There is an important another concept that I have to discuss here, which we will use little later, is the concept of effectiveness. which is basically denoted with epsilon. So you can basically define effectiveness as the heat transfer that is actually happening divided by the maximum heat transfer that is possible in that particular configuration. So in this particular case, Q is given by m dot Cp times T wall minus Tm outlet. Sorry, m dot Cp times out minus in, which is Tm outlet minus Tm inlet. So Tm outlet, this is the actual heat that is transferred from here to here. As the water moves from here to here, Tmi is the inlet temperature, Tmo is the outlet temperature. So m dot Cp times delta T will give you the net heat that the water absorbed from the steam. So this is the actual heat that is absorbed. What is the maximum heat that this particular configuration can absorb? So this particular configuration can actually take heat till the outlet temperature becomes equal to wall temperature. So this is the maximum amount of heat that this particular system can take. Only because I have reduced the length to around 61, instead of making infinite, the actual heat is little lower than that. So this particular term is called the effectiveness, the ratio of the actual heat that is transferred to the theoretically possible heat that can be transferred in that particular configuration is what we call effectiveness. Remember this concept and we will use it little while later. Are there any questions? Okay, we'll take a simple problem, one more thing, just to highlight the concept of what hydraulic diameter is. So because we are, in case of external flows, when we have a single plate or something like that, we have a characteristic length which is directly the length of the plate. However, in internal flows, we can have different cross sections. You can have square, rectangle, triangle, different cross sections are possible. You can even have configuration like this where you have, let's say, a tube, and then there is this thin wall that is separating two sections of the tube that is running through the particular cross section. So how do I define the hydraulic diameter? Hydraulic diameter is basically defined as 4 times area. Area is the total area through which the flow is happening. So it is the cross section area across which the fluid is flowing divided by the wetted perimeter. Wetted perimeter is basically the, you have to calculate at any given cross section. So if I have something like this and I cut it at any given cross section, then you have the fluid touching different surfaces. So you draw a contour for that, and from that you can calculate the perimeter. That is going to be the wetted perimeter. Area is the area through which the flow is happening. So in this particular problem, if you see, the area through which the flow is happening is the bottom and the top halves. So the area is basically pi d square by 8 into 2. So when I'm writing area like this, I'm basically assuming that the thickness of this particular wall that is separating both of them is negligible. So under that particular case, area will be same as whatever you have when you have a circular cross section. And wetted perimeter is where the difference actually comes. So the normal perimeter is pi d plus, because I have a wall, the fluid is now touching two different surfaces on the tops, on left and right of this particular surface. So on the left side, the total length is going to be d, and on right side also this is going to be d. So now I have this as my wetted perimeter. So from this I can calculate my hydraulic diameter. This is a simple problem as long as this concept is clear to you. Why we are using hydraulic diameter is because we can have different cross sections and fluid can have. And why do we need to introduce a concept of wetted perimeter? It's because your friction, the total friction that you're going to have is going to depend on the total contact between the fluid and the solid. So we have to consider the area in such a way that we account for all the surfaces where the fluid and solid are touching each other. So that effect is considered in the perimeter, and area is just to account for pressure drop, which we will discuss little later. We'll discuss in the next week. So, but for now, I think how to calculate this is clear. Are there any questions? There are no questions, then we'll move on to the next problem. This is where the concept of effectiveness that I introduced little while, you can use that and solve it yourself. A water chiller passes a stream of 0.1 kilogram per second through a pipe immersed in a bath containing a mixture of crushed ice and water. So previous problem is a condensation. Now we have melting. Because it is ice and water, you can assume the pipe to be at constant temperature at 0 degrees Celsius. The original inlet temperature of the stream is 40 Celsius and specific heat of water is also given to you. If the effectiveness of the heat exchanger is 0.85, calculate the outlet temperature of the water stream. So you have a pipe and the inlet velocity is inlet mass flow rate is given as 0.1 kg per second and it is coming at 40 Celsius and these walls are at 0 Celsius throughout. So it is a UWT case, uniform wall temperature case. Now the first part of the question asks you to find the outlet temperature. So as we already defined for the first part, effectiveness is basically defined as the ratio of the heat that is actually transferred, which is the actual outlet temperature minus, I'll just write TMO, which is a bulk mean fluid temperature at the outlet minus the inlet temperature divided by for a uniform wall temperature, the maximum heat transfer will happen when the outlet temperature will be equal to the wall temperature. This will be TW minus inlet temperature. So from this I can calculate my outlet temperature, which is a straightforward one. In our case, the inlet temperature is 40 Celsius, effectiveness is 0.85, wall temperature is 0 minus 40. You can check if you are getting the same value. Now we'll move on to the next problem, next case where you have what is the overall heat transfer between the stream and the ice water bath. This should be straightforward, right? You can apply an energy balance across the entire pipe and then calculate this. How do you do that? So basically the net heat transfer rate is given by m dot Cp times outlet temperature minus inlet temperature. M dot is already given to us. Cp is also given to us. So you have converted the units. This is joule per gram Kelvin. So you have to convert it to joule per kg Kelvin times the outlet temperature minus inlet temperature. And the negative sign is basically because this is losing heat to the ambient, to the surroundings. This is a straightforward one. So last one is an actually interesting one where let's say the pipe length is L, diameter is T, the flow rhythm is fully developed laminar. We are assuming that it's still in the laminar region. Now instead of this pipe, now I have to replace the pipe with a pipe that is half the diameter of it, maybe because of space constraints or because of some other reason. I have to reduce the diameter to half of whatever I'm currently having. But the effectiveness should remain the same. Then what should be the length of the new pipe relative to the old pipe? Take a couple of minutes and then we'll discuss. So how do you solve this? Where do you start for this? So where do you start for this kind of questions? We already know one relation before where we established that the temperature difference which I have derived a little while back is this particular relation where the length is related with the temperature difference in the logarithmic mean temperature. So we can use that concept here, from which we already know that the wall temperature minus, in this case, the other way around, the mean temperature at the outlet minus wall temperature by the mean temperature at the inlet minus wall temperature is given by. So now when if the effectiveness is constant, then so this particular term I can rewrite as is basically 1 plus epsilon. Is this step clear? Yeah. So you can see this term here. Sorry, I should have written the other way around. So this is 1 minus epsilon, sorry. So you can see this term is epsilon. So you have TMO minus TMI by TMI minus TW. So this is TW minus TMI. So you have a 1 minus epsilon. So when epsilon equals to 0, this will be equal to 1. Otherwise, it keeps reducing. So now we are saying in the question that you have to change the length in such a way that the effectiveness remains unchanged. So epsilon is constant. So which means this entire term is constant. Now we'll have to see what these individual terms are. So the mass flow rate that you are keeping in is also held at constant, which is zero point 0.1. Cp is also a material property which is constant. And as we discussed before, for a fully developed flow, H is also a constant. So m dot is constant because we have to maintain similar flow configuration. Cp is a material property which is constant. And H is a constant because we have the assumption that it is a fully developed laminar flow. Because all of these are constant, which means P should remain constant, where P is the total, sorry, this is P times L. So P times L has to be constant, where P is the total perimeter and L is the length of that particular one. So which is pi times D times L is constant. So from which we can basically write D into L should be D1 times L1, and it is already given D1 is D by 2, so which means L1 by L is D by D1, which is 2. So you can also see this intuitively that if I am reducing the pipe diameter by half, then I have to double the length of the pipe in order to get the same amount of heat transfer, so that the final temperature will reach the same value as if it was in the previous case. But what is the problem I will be getting because of this? So now in order to achieve the same amount of heat transfer, I have two possible configurations. I can either use the current configuration, which is the T comma L, or I can increase the length of the pipe and reduce the diameter of it and still get the same heat transfer. So which of these two configurations will be useful? So in order to answer questions like that, which we will discuss in next week, is where we have the trade-off. So if your the diameter of the pipe reduces, then your pressure drop increases. And then we also have another thing, but that when, as your length increases, the total surface area increases, which means your heat transfer can actually increase with that. So how do you decide which one? Is depends on the benefit you are getting because of the heat transfer versus the cost that you are incurring in order to get that particular flow rate. That trade-off will actually decide which particular configuration of DCAM that you have to be using in your particular problem. We will take up a problem on that once we derive the correlation for Nusselt number, which we will do in the next week. But other than that, is this clear? Are there any questions? Okay, now let's take a numerical problem, which is a fairly straightforward one. These are the kind of problems you can expect also in your assignments and quizzes, assignments in your exams. So where you have, they will give you a certain kind of a velocity profile and a temperature profile. You can measure them experimentally, or you got some way using analytical techniques. Now the question now is you'll have to find the mean temperature at some particular position. Where here it is in the axial position, which means you have to do that at r equal to 0. This is more of an mathematical exercise. So I think you'll be able to solve it. Maybe it will take little more time to do the integration. So how do I define? First, we have to write the equations for both of them. So where we have this is u of r, this is t of r. So the mean velocity is given by, and then the mean temperature is given by. This is more of an analytical exercise. So maybe you can take 5 minutes to solve this. Start with the first one. Did you get the answer already? So you can basically transform the variables in such a way that you consider r by r naught as x or something, and then you can write this integration. So dr will be r naught times dx. So this will be r naught times 0 to 1, 0.1 times 1 minus x square x dx. R is r naught into x, so dr is r naught, so you'll have an r naught square here divided by r naught square into 0 to 1 x dx. So this will give me 0.1 integral 0 to 1 x minus x cube dx divided by integral 0 to 1 x dx, which is 0.1 times 1 by 2 minus 1 by 4 divided by half. So that comes around 0.05 times r naught, 0.05. Is this clear? Now similarly we can also calculate the Tm value, which is again the same kind of transformation we use. So we have an r naught square on the numerator and denominator that I'm kind of removing. So we have 0.1 times integral this entire quantity. Okay, first integral 1 minus x square into, for t we have minus 18.8 x to the power 4 x dx divided by 0.1 into integral 0 to 1 x minus x cube dx. So once I do the integration, I'm getting this value around 366.68. You can also calculate and let me know if you're getting the same value. This is more of an analytical derivation. As long as you know the thing and like know how to do the integration and then write the equation correctly, then there are no problems in solving this problem. Are there any questions? Okay, if there are no questions, then we can move on to the next problem. Consider a cylindrical rod. So this is a cylindrical rod of length L and diameter D. The inner diameter is D. This is D. That is encased in a concentric tube. Pressurized water flows through the annular region. So between the tube and the outer one, you have this is an annular region inside which the fluid is actually flowing. That is a coolant. So this fuel rod is in some kind of a nuclear fuel rod that is getting heated up. There is an internal heat generation, and that is given by Q naught into sine pi x by L. So here you have 0, here you have 0, and the heat generation is going like this. So because of the heat generation rate, there will be a temperature difference, temperature gradient along temperature gradient on the surface, and then you will also have heat flux variation along it. So what we are trying to find now is, first we have to understand what is the wall temperature, which is the surface temperature of the fuel rod, what is the local heat flux that is happening on the fuel rod, and then we'll also answer what is the mean temperature of the fluid inside the annular region. These are all questions that we need to solve for. Okay, first start with the first problem. How do I find the local heat flux? Like, first problem has two parts. First, determine the local heat flux, and second, you have to find the total heat transfer from the fuel rod to the water. Water is basically our coolant. So how do I solve this? So first we'll observe that this particular process has reached a steady state. So the net heat flux that is generated at any cross section should be equal to the net heat transfer that is happening to the water. So if I consider any small cross section, where the net heat generated is given by Q naught sine pi x. Maybe first I'll draw this little cross section. So I have a fuel rod. This is some cross section, and then I have this is my annular region, and this is my water. So the first one is the heat is generated within the fuel rod. So the net heat generated will be Q naught times sine pi x by L at that particular cross section into the volume of the fuel rod. The volume is given by the area of cross section times the length. If this length is, let's say, dx, area is pi d square by 4 times dx. This is the total heat flux that is generated within the rod. If we assume that there is no axial conduction along the fuel rod, this entire heat flux that is generated will have to be lost to the coolant through top and bottom. So that will be H times, or the local heat flux on the surface of the fuel rod is Q double prime, is what we are asked to find. The heat flux times the total surface area from which the heat loss is happening. That surface area will be this and this surface area. So the total surface area will be pi d times, pi d is the perimeter, times dx, right? So from this we can estimate Q double prime, which is the local heat flux. Right, this is fairly straightforward. So the only assumption that we are making here is neglecting the conduction along the fuel rod. Otherwise, we have to also have to account for what are the conduction losses that are happening along the length of the fuel rod, which we are neglecting in this particular case. Okay, now the second part of the first question asks you to find the total heat transfer from the fuel rod to the water. How do we do that? Yeah, like what we have to do is just integrate the total heat flux. So the total heat transfer is given by integral of the surface heat flux at any x location times the surface area, which is pi d times dx, from 0 to the total length of the rod L. This is a fairly straightforward one. So all you have to do is substitute this equation back in this, which will give you so this will be Q naught times pi d square by 4 times integration of sine pi x by L is L by pi minus cos pi x by L between 0 to L. That will give you Q naught dl by 2. Sorry, d square L by 2, right? This is a fairly straightforward one. So basically the idea, you can also think of it in a different way, where you are saying that the total heat generated within the fuel rod has to be dissipated into the fluid, because the external wall is completely insulated, so there is no other way for the heat to go, and we have neglected the axial conduction part. So you basically have to do what is the total heat generated within the rod, which is the volumetric heat generation times the volume of the differential element that we are considering, which is pi d square by 4 times dx. So once you do the integration, you will get the net heat flux. This is a straightforward one, right? Any questions in this? Okay, then we'll move on to the second part. So the second part of the question asks you to find an expression for the variation of the mean temperature of the water with the distance x along the tube. Now how do I find this? This is also a simple one where we have to do the same analysis as before. We'll take the same differential volume that we have considered. So we have this length as dx. Now some water is coming here and leaving from the other side. So what we know is if the mass flow rate of the water is m dot times Cp times the differential change that we're having dTm. This is the net heat flux, the net heat that is absorbed by the water. This should be equal to the net heat that is rejected from the fuel rod, which is Q naught times this is the net heat generated into the differential element, the differential volume, which is pi d square by 4 times the length of that small element, which is Tx. So now all we have to do is integrate this equation and get an expression for Tm. So we know the inlet temperature is Tmi. To some distance m x we have dTm, which you can solve from here. Take a couple of minutes, solve and tell me the expression for Tm you are getting from this. Did you get the answer? So if you want to integrate this, from this you can get the expression for bulk fluid temperature at any position x as the inlet temperature, and you can see that it should be varying sinusoidally because the heat flux is also varying sinusoidally. Q naught dl m dot Cp right? Any questions in that? Okay. Then we'll move on to the last part. So now what we are asked to find is develop and obtain an expression for the variation of rod surface temperature with the distance x along the tube. Develop an expression for the x location at which this temperature is maximized. So first let's solve the first part of the problem, which is a straightforward one. So we know the temperature difference, so we can calculate. So we already know that the heat flux, the heat transfer coefficient times the surface area times the surface temperature minus Tm should be equal to the net heat flux times the surface area. So from this we can calculate Ts, because Tm we already have the expression. So Ts is given by Tm plus Qw prime is the net local heat flux divided by the heat transfer coefficient. So if I substitute that back, I have Tmi plus, plus we have one more term because of this H, which is, so this is a straightforward one. It's basically substitute the value of Tm that we already got from the previous expression into this equation, which is a straightforward one. So there is nothing much difficult in that. So Qw prime you already have the expression, Tm we already have, so just substituted them back into this equation, the one that we got from A and B, and then we got the first part. The next part of the question asks you to find an expression for the x location at which this temperature is maximized. So as we know that the heat is actually increasing sinusoidally and then sinusoidally, which means it increases initially and then it reduces here, the heat generation, which means there will be a point where the temperature will reach its maximum value. And how do you determine that is, in order to obtain the maximum value, you have to take the derivative of that and equate it to 0, which will give me, right? Now you can solve this expression. So this is basically sine pi x by L plus, and so from this we can calculate the value of that, which is give us, right? So depending on the heat transfer coefficient and the mass flow rate that we are having, that determines where the maximum value of this temperature is going to be. So this is a straight, simple analytical one. Are there any questions in this? Okay. There are no questions, and I think these are the questions I have for this week. So next week we will be discussing on the same internal flows that we discussed this week, but then we'll also derive the correlation for Nusselt number. We already found that the Nusselt number is going to be constant under fully developed conditions, but we just have to figure out what the constant value is going to be, which we will discuss in the next week. And that value is going to be different for both the uniform heat flux, uniform wall temperature. And again, we will also discuss parallel plate channel flow versus the circular pipe flow, annular regions, and different cross sections, how the constant value changes, and how is it related with the Reynolds number, Prandtl number, and all that stuff is what we will be discussing in the next week. Again, we will be discussing, as we said initially when we started this course, we have the fully developed case, developing flow. So first we will start with a fully developed one, and then we'll also take a simpler one called as slug flow model, and then we'll move on to developing region. Towards after we complete fully developed, we'll also see developing region, and then we will see how what are the criteria that I can use to decide whether I'm in the developing region or the developed region, and then we will conclude the internal flows. Once these both of these are done, then we will move on to natural convection. That will happen in the next week. Yeah, thank you for joining. And if you do not have any further questions, then I think we can end the session for today. I think there are no further questions. Okay, then we'll end the session for today. Thank you for joining.